Okay, I've arranged the program in what makes sense sort of from a conceptual point of view. So you just heard about why we can't forecast more than a few days in the future. And the rest of the talks will talk to some extent about why we can. Because the atmosphere is not just sitting there by itself, it's interacting with other things which are predictable in themselves and help us understand to some extent what's going to happen to the atmosphere as a result of that. The next speaker is an expert, among other things, in atmosphere-ocean interaction. His name is Ramalinghan Saravan. He's a graduate of Princeton University. He spent his time in Cambridge, but not on this side of the ocean, the other side, and also at the National Center of Atmospheric Research. And he does work in atmospheric dynamics as well as land-ocean interaction, specializing in computer modeling. Saravan?
Okay, I'm going to talk about the interaction between the atmosphere and the ocean and how we can use that to do short-term climate prediction. And by short-term, I mean a season to a few decades. So I'm not getting into climate change, which has other issues. But here we're talking about a time scale where carbon dioxide changes are not that important, but some other things are important, and we'll talk about that. Next slide, please. So I'll show an engineer's slide first. This is a picture from a car or any automobile engine. And what you see is the crankshaft. And there are 4 pistons. It's a 4-cylinder engine here that are driving the crankshaft. And there's a big wheel on the right that's called the flywheel. And it's there in most cars. And what happens is each time the cylinders fire, it creates an explosion and it's a jerk. But it pushes the flywheel and the flywheel moves smoothly. And the same thing happens when you ride a bicycle. You push on the left leg, on the right leg. You don't go in jerks like this. You move smoothly because the flywheel is the bicycle itself. It has mass and moves smoothly. So what the crankshaft and the flywheel show you is that you can have small jerky motions, but if there's something with a lot of capacity, momentum capacity, mass, the result can move smoothly. And if you stop the engine, the flywheel still keeps moving till friction or something else stops it. So it gives you extra memory or time. Let's go to the next slide, and we'll see an animation of what this looks like. So you have the cylinders firing in a car engine and the flywheels moving smoothly despite the jerky motion of the cylinders. And there's an analogy here. The jerky motion is like the atmosphere, and the smooth motion is like the ocean. So the atmosphere, the weather systems in the atmosphere that Dr. Junior talked about, they're random and stochastic, but they move the ocean much more smoothly. And the analogy here is slightly different in the atmosphere and the ocean. In the actual crankshaft, it's the momentum that's being transferred from the pistons to the flywheel. In the atmosphere-ocean interaction is the heat. The atmospheric weather systems put heat into the atmosphere, and that heat is stored in the ocean and released over time. So it gives you a much longer time scale. And as Dr. Nielsen Gammon pointed out, we can't predict atmospheric weather beyond 2 weeks, but we can predict something else beyond 2 weeks. And that's the flywheel, which we can predict out to a few months to a few years. Next slide, please. So I'm going to talk about the climate system. So we're going beyond the atmosphere here. And the climate system consists of the atmosphere, the ocean, land, and ice, and a few other things. But these are the big ones here. And the ocean acts like a flywheel for the climate system, providing memory from atmospheric random stochastic phenomena. And the ocean and the atmosphere interact over all the globe, but the strongest interaction occurs in the tropics. And I'm going to focus on the best example of such interaction. It's El Nino, which is something you've all heard about. I'll briefly talk about what it is. And although El Nino happens in the tropics, what happens in the tropics doesn't stay in the tropics. And that's very important when it comes to seasonal to multi-year forecasting. Next slide. So here's what El Nino is. On the left, you see temperatures of the ocean surface, called sea surface temperatures. And at the bottom is a color scale. It shows how big it is. And anomalies are in degrees Celsius. The Celsius is about 2 Fahrenheit. So there are times when you get 2 to 4 degrees Celsius anomalies in the tropical Pacific that you see there off the coast of Peru, which you don't see. But in the tropical Pacific, you see these warm anomalies. They occur about every 4 to 5 years, and they have the name El Nino. And the opposite phenomenon occurs also, and that's what's on the right. It's called La Nina. But the important thing is during El Nino, you get warmer than usual temperatures. It's warmer by 2 to 4 degrees Celsius, which is a lot in the tropical ocean. Next. So what happens when you get an El Nino is that it changes the rainfall patterns in the tropics. What you see on the top, again, you see on the left is Australia. You can see portions of Australia. On the right, you see portions of South America, Central America, and North America. And in between, it's the Pacific Ocean. And the red part is the sea surface temperature anomalies that you saw. In the normal conditions, the warmest temperatures occur near Indonesia, off the coast of Australia. And the rain occurs where the warmest ocean temperature is, because there's more moisture, there's more rain. When you have El Nino, you get extra warmth near Peru, and the whole rainfall pattern shifts to the right, to the east, and so the rain and the clouds move to the center of the Pacific rather than staying at the western part of the Pacific. So the change in the rainfall pattern, it's a big deal in the tropical Pacific. And it also changes the ocean, and what's shown below is what's called the thermocline that divides the upper ocean from the lower ocean, and that changes its structure when this happens. And that's where the memory in the system is created. Then when atmospheric patterns in the rainfall change, it changes the winds on the surface, and it changes the ocean thermocline, and the ocean has a lot of heat capacity. 2.5 meters of the ocean has as much heat capacity as the entire atmosphere. So that ocean's about 4,000 meters deep. So you can imagine the amount of heat in the ocean is 1,000 times more than the amount of heat you can store in the atmosphere. So it's a huge amount of memory. So what can we do with this memory information, and how does it affect us, for example, in Houston? Next slide. So here's an example. There's a duck swimming in a pond, and it's creating waves. But we're standing at the edge of the pond. If you wait a bit, you'll see the waves. The ripples come by. They'll be weaker, but once the ripples start in the pond, the waves come out and they propagate out. And the same thing happens when the rainfall patterns shift in the tropical Pacific. They create atmospheric waves. They're called Rossby waves. And these Rossby waves propagate out. And they take, the pond waves might take a minute or less, but the Rossby waves take about a couple of weeks. It's pretty fast for the atmosphere. So within a couple of weeks after the rainfall pattern changes, you'll see start seeing effects in North America. The North American rainfall patterns change because these waves propagate out from the tropical Pacific. So even though the memory in the system is in the tropics, these waves expand this effect all over the globe. And we'll see that in the next slide. So this shows the impact of El Nino all over the globe. You can see that we have effects in North America. When you have an El Nino, you have less rain in the Northwest, like Oregon or Seattle. You get more rain in California. You have less rain in the Amazon region in northern Brazil. And you have weaker monsoon in India when you have El Nino. So you have a global effect due to these propagating waves emanating from the shifting rainfall patterns in the tropical Pacific. And it also depends on the season what the effects are. And this wet effect of El Nino in California, for example, becomes very important because right now we have a drought in California. And one of the big questions now is, and it has been since April, is there going to be an El Nino? And people in California want an El Nino because whenever there's an El Nino, the jet stream shifts and brings more moisture into California. And what we'd like to do is to be able to predict in advance whether this is going to happen. Go to the next slide. So to predict El Nino, we use computer models. Dr. Nathan Gammon talked about that. We use mathematical equations to do that. And this is a pictorial representation of what a model looks like. We take the atmosphere and the ocean, because that's where the memory is, and land. You'll hear more about land next time. And ice. We put a grid on it. And right now, the grid boxes that you put are about 50 kilometers in the horizontal, in the north, south, east, west, and about 500 meters in the vertical. It's still a millions of grid boxes. It's still not enough. But if you look at a cloud is about a kilometer or two. So we still can't resolve clouds in our grid boxes. That's one of the limitations. But as our computers get more powerful, these grid boxes shrink. And maybe in 5 to 10 years, we can actually do individual clouds simulated in our models. Next, please. We need a computer model. We also need initial conditions. And in the ocean, the initial conditions are hard. The initial condition is the state of the flywheel. Is it spinning fast? Which way it's spinning? We need that so we can predict what's going to happen next. And this shows our current state of ocean observations. The green are deep buoys, moored buoys, which transmit real-time data. You can go to a website and get real-time data on the state of the ocean up to a couple of thousand meters below the ocean surface. So we take this data, put it in the computer models, and run it out and see what happens in the next month or the next 6 months or next year, and that's how we make forecasts. And one of the limitations right now is the sparse coverage. There's not enough coverage in the ocean to know the initial state of the flywheel. The better we know the state, the better we make the forecast. Next, please. So what's happening right now, this is the forecast for El Nino that I picked off the web. It was made 10th November, 2 days ago. In April, they actually predicted a fairly large El Nino based on the ocean state at that time. And right now, the forecast has been weakened to modest to weak El Nino. And the way these forecasts are done, we take the average of surface temperatures in the ocean over a small region. That's a rectangle. It's called Nino 3.4. It's in the middle of the Pacific. We plot a time series of the value of temperature average there. And you can see this is what we've seen in the last year or so. Starting from January, we had cold temperatures. In April, the temperatures warm. They're about 0.4 to 0.5 degrees. And that's when people expected maybe an El Nino is going to begin. It cooled a bit in August and picked up again, and it's still about 0.5 degrees in the Pacific. We put this information, not just this region, but the whole coverage in all the points we saw before. We do a forecast, and this shows the predictions as of 2 days ago. And the y-axis is temperature in this region, and the x-axis is 3-month averages. The AMJ is April, May, June. MJJ is May, June, July, and so on. So where the line spread out, that's the current moment, that's November. And you see a spread, that's uncertainty in our seasonal forecast. So there's uncertainty, but the average forecast is a dashed line. And that says most likely there's going to be moderate El Nino, about 0.5 degree. So it probably isn't going to solve California's problems, but it could mitigate it. And again, we keep revising these forecasts as time passes and we get new information. Next slide. So to summarize, the memory in the climate system can be used to make short-term climate predictions, seasons to decades in advance. And accurately modeling the climate system, having a better model, having smaller grid boxes, and also observing the ocean state, because that's where the memory is, more accurately, can help improve the quality of our forecast. Thank you.